So in this video, we're going to talk about the relationship between equilibrium and Gibbs free energy. Earlier in this course, we learned about this concept of delta G, or the change in Gibbs free energy. All right, and essentially that's what drives a reaction. All right, so I'm not going to get into the all the specifics of this, but you should be familiar with this common reaction right here. The delta G is the equal to the change in enthalpy minus T delta S. All right, where delta S corresponded to change in entropy, which you can think of as a measure of the randomness or the disorder of a reaction. And change in enthalpy is essentially a measure of whether heat is either released or absorbed by a reaction. All right. And one thing that we learned was that whenever you have a negative delta G, that's essentially going to mean that the reaction is going to have a tendency to spontaneously proceed towards the right, or from reactants to products. All right, so from left to right. If you had a positive delta G, that would mean that the reaction would spontaneously proceed in the opposite direction. All right, so from right to left in the direction that it's written. All right, but if your delta G was 0, that means that there wouldn't be essentially that would mean that it wouldn't want to proceed in either direction. So what we're going to do in this video is talk about this in light of what we now know about equilibrium. All right, so what we now know about equilibrium is that when you're at equilibrium, essentially the concentrations of the reactants and products want to stay the same. All right, so at that point, there's really no tendency for the reaction to either go to the left or to the right. All right, so because of that, we can conclude that at equilibrium, and this should say delta G equals 0. All right, so that's going to be something that's true. Again, you need to write in equals 0 there. All right, so we're going to apply this to some actual cases. So in these two graphs, all right, let's pretend that we have just a very simple equilibrium. All right, A can go back and forth with B. All right, and the y-axis is going to represent free energy, and in both cases, we're going to have the left position will be 100% reactants, and the far right position would be 100% products. All right. So if you measured the free energy, all right, as you go from all reactants to all products, we know that there's going to be some position where we're going to have equilibrium. All right. So how does that relate to free energy? That's going to result where you have a minimum value. All right. So but notice that there's a difference between these two graphs. All right. Here, that equilibrium position is more towards the product side, and here that equilibrium position is more towards the reactant side. All right. So whenever you have, this is going to be the type of graph that you would have if your equilibrium constant was greater than 1. All right. And the reason for that, whenever it's greater than 1, if you write your equilibrium constant, that means you have a larger numerator than denominator. So that means that that position would be closer to the point where you've got higher amounts of products. Right. So note that in either of these positions, if you started off with 100% reactants, all right, the reaction would start off with a tendency towards going towards the right until it reaches that equilibrium position. All right. So the point of equilibrium corresponds to a point, and this is pretty important, that corresponds to a minimum value of Gibbs free energy and also a maximum value in entropy. All right, so from these graphs, it's pretty easy to see how it corresponds to the minimum value in Gibbs free energy. But for now, we're just going to have to take for at face value the fact that this position of equilibrium would also correspond to a maximum value in the overall entropy of the reaction. All right, so remember that delta G is a change in the free energy. All right, so one thing that should be that you can see by looking at these graphs is the amount of free energy that you would have at the very beginning of the reaction, or the amount of potential for a change in the free energy is different at this point in the reaction than it would be at this point in the reaction. All right, and that's because there's more energy that can be free energy that can be changed going from here to here than there is from here to here. All right, so to make an analogy, Let's think of the equilibrium position of this spring as just being the point where it naturally wants to be. All right, and but the thing is, this is not necessarily the where the actual length actually resides. All right, so we can change this position by a certain amount. All right, we know that when things are out of equilibrium, they want to get back to the equilibrium position. All right, and so intuitively, it would seem that there's some amount of energy change that would be involved in getting from whatever it currently is at towards back to that equilibrium position. All right, and it can go either way. We can go from the too short side where it bounces back this way, but we could also go back from the too long side going back this way. All right, so we can make the analogy that that would correspond to one side would be if you're too far on this side of the equilibrium, and one would be on this side of the equilibrium. But consider this. This position right here, would it be the same amount of energy going from a really long spring back to the equilibrium, or would that be a different amount of energy if you're going from just slightly longer back to the equilibrium? All right. So obviously there's going to be more energy that would drive the process in going from way out of equilibrium back to the equilibrium than if you were just slightly out of the equilibrium. So if we wanted to have a full description of the delta G for a reaction at any given point in time, there's actually two parts to it. All right, there's going to be a part that describes the intrinsic nature of a particular chemical reaction. All right, for example, if we have a equilibrium reaction and we have a equilibrium expression, we need to know where that equilibrium is so that we can judge how close we currently are to it. All right, so it's kind of like saying, if I were to say, just show you the stretch spring and say, well, how much energy could this give off? All right, well, I would have to know what it would look like in its equilibrium position for me to know how much energy is in this stretch spring. All right, without knowing that, I can't make that determination. All right, so we need to know that. But there's also something that we need to know is what the current concentrations are, because just knowing what the equilibrium position is going to be meaningless unless we know how far from that equilibrium position we currently are. All right, if we are currently at that equilibrium position, there is going to be no delta G. All right, delta G is going to be equal to 0 in that case. All right, but the farther, essentially, if this was the situation we're dealing with, the farther we are away from that equilibrium position, the more potential delta G there is for that reaction. All right, so we need an expression that captures both of these. All right, and so these concepts are put together in the following expression. All right, delta G equals this delta G with the degree symbol. We'll talk about what that is in just a second, plus RT ln of Q. All right, so first of all, delta G is going to be obviously the delta G of a reaction, but it's important to note that is for an actual set of reaction concentrations. All right, this delta G with the degree symbol, that's called the delta G, or the standard state delta G. All right, and so what that is the delta G of the reaction under what are considered standard conditions. All right, and what is meant by standard conditions is a situation where the concentration of all reactants are 1 molar, or if we're talking about gases, all right, all the gases would be at 1 atmosphere of partial pressure. All right, so by the way, when we do redox reactions in electrochemistry, we're going to revisit this concept of standard conditions because it allows us to do some fairly useful things. All right, and so there's also this part right here. All right, so what this part right here is essentially a part of the equation that adjusts for what the actual concentration of the reactants are. So remember, this would be essentially what the delta G is if all the reactants were at that concentration right here. But in reality, if you look at this right here, you could be at any point, not just where you have exactly 1 molar of all the reactants and products. You can have any combination of these. All right, so if we're going to calculate the real delta G, it's not necessarily going to be the delta G when it's at those special concentrations. In fact, it's highly unlikely that it will be at that specific condition. All right, and so what this does is it adjusts for that what the actual concentrations are. All right, and remember Q is the reaction quotient, so that's an expression that will plug those actual values into. All right, R stands for your gas constant, and T is your temperature expressed in Kelvin. All right, so to better understand how this works, we're going to talk about this under a couple of special conditions. All right, so first let's think about what would happen if the reactants, or the concentration of all the reactants and products, were at standard conditions. All right, so remember what Q is. All right, it is going to be it's the reaction quotient, and recall that Q can, depending on what your actual reaction is, might be more complicated than this. And in fact, sometimes it has a squared term, sometimes it's multiple things that are multiplied by each other. But remember that under these standard conditions, all of these concentrations are going to be 1. All right, so if you square a 1, it's still 1. If you multiply 2 1s together, it's still 1. If you divide something by 1, it's still 1. All right, so because of this, whenever these are at standard conditions, Q is always going to be 1, because no combination of squaring these, or multiplying these or dividing these, will give any number except for 1. All right, so therefore ln, the ln of Q, is going to be the ln of 1. All right, so that value right here will be 1, and the ln of 1 is 0. All right, so at standard conditions, your ln of Q is going to become ln of 1. All right, and the natural log of 1 is 0. And so this part of the expression right here becomes 0. And so delta G is going to essentially be delta G at standard conditions. And this should make sense, all right, because that's what delta G at standard conditions is. All right, so essentially we've just proved what we should have already known, is that the delta G of the reaction at that special condition where all of these are, all the concentrations are 1, are really what the delta G is for that special set of conditions. All right, so the next situation I want to consider is what happens if you've got a reaction that is at equilibrium. All right, so recall that at equilibrium, that's when your delta G is going to be 0. All right, so remember that's the position where there's not a tendency to want to go to the left or to the right. All right, there's no reason for it to change, so the free energy change at that point would be 0. All right, so also if you have equilibrium, that means that your reaction quotient is equal to your K equilibrium. All right, so we can take the same reaction that we had before, and what we showed here is that your delta G is going to be 0, so I can plug that in here. And your Q is equal to your KEQ, so I can plug that in here. And just rearranging things, we get this equation right here. All right, and this is going to be a very useful equation. All right, and before going on any further, I just want to point out that this equation right here is found right here in your data booklet. All right, so we're going to talk a little bit more about this equation in the next video.